Okay, good afternoon, everyone. So let's get started. Let's get started the afternoon session. So we have a really great pleasure to welcome Dr. Gareth Conduit from the University of Cambridge to deliver the first talk in the afternoon about the modern day blacksmith. So I'm really looking forward to learn how the blacksmiths will work in modern days. So just give you a bit of introduction of Gareth. So Gareth has a very strong track record of applying artificial intelligence to solve real world problems. I think that fits very well with the IAS themes. It's really to see how artificial intelligence is developed in the lab, but is to use to solve a real world problem and to deliver impact and the value beyond the lab or beyond the academic community. And that's exactly Gareth is doing. And Gareth's approach, I think, originally developed for materials design, but now has been successfully commercialized through his startup called Intelligence, and has been now extended to a very wide range of applications, not only in materials design, but also in the pharmaceuticals and different applications, which Gareth, I think, will cover a little bit in today's talk. And I mean, beyond Gareth being a very successful in running the business, he's also a Royal Society research fellow at Cambridge, and his background is in physics. So that's another thing that I'm really interested in to know how, like, a scientist, like chemists or physicists, develop themselves into that very emerging area of artificial intelligence, and to combine the artificial intelligence as a tool with the theories, I mean, with the science theories, I mean, physics, science, or engineering, or whatever, to deliver the real world solutions. So without further ado, Gareth, the floor is yours.
No, thank you very much, Jean, and also thanks to the IAS for very kindly inviting me to be a fellow this week. I had a great time up in Luffa, organised much by Kieran back there, and it's also great to be down on your London campus. I really enjoyed looking around. So I'm also really excited to be able to share with you today the story about how we developed a novel machine learning phenomenology in the lab, and then have been able to take it out into a startup to really try to maximize the impact of the work that we developed. Now, oh, there we go. I'll use that. Right, yes, so we've been developing our machine learning technology to work initially on materials data, but more widely on sort of real-life experimental systems. And one thing that all these data sets these systems are going to have in common is that the scientists always, or engineers always, want to optimize multiple things about the material. They never want to find the strongest material in the world, because that, well, hardest, because that would be diamond, but diamonds might be too expensive to actually be useful in real life. But instead, they want to be able to optimize the materials, chemicals, drugs, to have a whole slew of properties, and they must satisfy all of those simultaneously. Now, this means that we're going to need to get the data to train our machine learning from many different sources, and we're going to find for each material some things have been measured, but other things not, and the next material, maybe the latter were measured and the former not. And this means that our underlying data sets are always going to be sparse. And sparsity is going to be a real problem for machine learning, because machine learning is a formula and it needs all the mathematical inputs to give an output, and it can't handle missing numbers. And so we're going to be developing our machine learning phenomenology to really thrive in these situations in which we have sparse data. Now, one way we're going to do that, a very strong ongoing theme, is to exploit the relationships between different material properties. So, for example, a hard material is often also strong. A material that is a good thermal conductor is often also a good electrical conductor. And those types of relationships we're going to really exploit, so we can use knowledge about one property to help infer the other, when it had sparse data. Now we're going to extend this theme. It's not just going to be property from experiments that we're going to take advantage of, but we're also going to merge together other methodologies for predicting material properties. So we've got listed here, for example, first principles computer simulation methods that have been developed, and also physical rules of thumb that scientists have known about for some time. We want to encompass all of that information so we can learn from everything we possibly can in order to make the best predictions. Now, once we've got our machine learning tool up and running and we can make good quality predictions, we're then going to be all set, and we're going to often use it in order to discover new materials. We're going to get our tool to scan through millions of materials and find the one that's most likely to work. And we're going to see that we'll be able to do that much more quickly than the contemporary approach of discovering materials, of a sort of trial and improvement process that might take 20 years to cycle around material space until you hit upon that right composition. And so from a commercial standpoint, we're going to accelerate the rate of materials discovery, and there's going to be a concomitant reduction in cost. Right, so I thought I'd have a quick outline here of how our machine learning works, and unlike what we were told about this morning, I have drawn a black box here that hopefully will make it more grey later, where we're going to start out on the left there with the ingredients for the material. So we've got here the composition, we've got little piles of different elements that we might consider putting in, so we need to specify how much of each one. And we've also got, as Professor Tanaka mentioned, the processing variables. So how long do we hold the material for at what temperature? And to make a successful material, we're going to need to get all of those correct. So that's a list of numbers. We're going to put it into our machine learning black box here. And then we want on the right it to magically spit out the different material properties that we're interested in. Now, I've got listed up here the number of defects that are formed in the materials. That's like the number of cracks and pores. We've got for the fatigue life, that's how many times you can stretch it and let it go and stretch it again before it snaps. And down the bottom, we've got the strength, how hard you can pull it. Now, for our black box machine learning tool here, there's lots of options that are available. We heard about several from Professor Tanaka, but perhaps one that we might consider using is a neural network. Now, this is a mathematical representation of how it is thought perhaps the human brain works. But one thing that it does have in common with a human brain is it needs to go to school, it needs to go to university to learn about the material system. And when it does that is just like the students, is to go and look at some historical information. Here we've got historical data about how related materials work, both the composition and some of their properties, albeit sparse. And we can take that data, we can feed it in, and you see we've now trained up that neural network. And then once it is trained, we can take the historical data away, we can change the composition, we can put in a new material composition that it's never seen before. And hopefully through the power of machine learning, it will make a prediction for those material properties. And then, of course, it runs in about a microsecond or so. So we get it to then scan through millions of materials until it finds the one that best satisfies the engineer's requirements. Now, in order to demonstrate how we're going to sort of do this in the real world, and in particular to see the big ramifications and ways we work around sparse data, I've got here one of the early case studies that we did, which is we worked with Rolls-Royce Group to develop some new alloys for their jet engine. So I have a schematic of such an engine. Here's the air comes in from the left, and then where it's blue, the air is compressed. And then where I've got that little orange box drawn is where the fuel is injected into the air, and the fuel burns, and as it burns, it gives off energy, it expands, and then it rushes out the back of the engine, which provides the thrust to push the plane forward. Now, Rolls-Royce are very interested in making the engines as fuel efficient as possible, be as environmentally friendly as possible. And one of the critical components is exactly where the fuel is burned. We've got a cutaway here, so you can see what the component looks like, where the fuel is injected. And you can see just from this cutaway that there's a very intricate shape. And that's so that they can get the perfect fuel air mixture, so they can burn the fuel as cleanly as possible, as hot as possible, to extract as much energy out of that fuel as possible to make the engine more fuel efficient. Now, this component up here is made by a combination of casting and other fabrication. But what Rolls-Royce would like to do is turn to a new manufacturing process. They'd like to use additive manufacturing or 3D printing, so that they can try to print that component to be even more intricately shaped to get an even better fuel air mixture. So I'd like to do that, but a big problem is that the alloy that they're going to use up here has to sustain some very extreme conditions. For example, the fuel being burned burns hotter than the melting point of the alloy around it. And there's a lot of pressure in that chamber, which ultimately provides the thrust for the engine. And so they need an extreme material that can survive those conditions. But they also now need that same material so that it can be very easily printed without any defects. And at the moment, when we entered this project, there's no material that would satisfy those different criteria. And so we were tasked by Rolls-Royce with using machine learning to see if we could design for them a new alloy that could be 3D printed and work well in the engine. So we got here to the schematic of the little bit of the machine learning that we will need to train to predict the ability for 3D printing, which I've got represented here by a sort of laser beam that melts the metal powder onto the component. And there's going to be an immediate and very significant problem. And that is that 3D printing this type of alloy is a completely new process. It hadn't really been tried before. And when we did the project, it had only been tried actually 10 times before for 10 different combinations of alloys and processing variables. So we had a total of 10 pieces of data here for how the quality you could print to. But unfortunately, the input parameter space over on the left, so that's the number of different elements we put in and the number of processing variables like the laser power and the laser diameter and so on, is 30-dimensional. And so when we're designing this alloy, we're going to need to specify all those 30 numbers, but we've only got 10 pieces of data available. So for even school level maths, we can see that's going to be impossible. You can't get 30 bits of information from 10. And so it appears we're sunk. And if the very simplest model you could make here is just to fit a plane, a hyperplane through those, for those 30-dimensional space, and you're going to need 31 pieces of data to fit a hyperplane. So you need 30 pieces to specify the gradient in each direction, and one more piece of data to specify the intercept, how up and down the plane is. And so it looks like this is going to be impossible. And of course, it's inevitable because this is a new alloy and it's going to be very common to most discovery projects. You're not going to have very much data. But this is where we're able to use some of our sort of additional, well, my colleagues' knowledge of material science and some of our intuition, and to notice that there are other processes that are similar to 3D printing. Now we can notice that over on the left, we've got this 3D printing where we are melting the material very locally, small bit of space, with a laser beam. Over on the right, we've got welding. And in welding, you melt the material locally with a high electrical current, with electricity. So essentially very similar, just the agent that's doing the heating is different. Electricity on one side and light on the other. And so we might ask, perhaps if an alloy was good at welding, then we would hope it would also be good for 3D printing. And we're lucky that welding is an older process. It's been tried a lot more on this alloy system. So we've got lots of data about welding. And so can we harness all of that lovely data to help tell us how well an alloy would perform for 3D printing? So this is exploiting exactly one of those property-to-property correlations. And so schematically, what it's going to look like, we're going to start out on the left with the composition of the alloy. We're going to go through our machine learning tool to predict how good it is at welding. For that, we've got about 1,000 data points available, and 1,000 is enough in order to understand quite a complicated landscape in 30 dimensions, to understand there's 8 jumps in it as you undergo phase transitions. Then in a second step, we've got a second machine learning model that goes from welding, and then behind the zoom interface here, there is the ability for 3D printing, for which we've got 10 data points available. Now, we're lucky that although 10 isn't very many, it's going to be enough, because effectively we're almost learning just a straight line from ability for welding to ability for 3D printing. And to fit just a straight line in one dimension, you need 2 data points to specify a straight line. So you fit a straight line through them. A third data point that lies on that line will confirm for you that it actually is a straight line, which isn't obvious. And so if you've got 10 data points or perfectly lying along that straight line, that's going to be plenty in order to learn a very good model to go from welding to ability for 3D printing. And so this is the trick. We're exploiting a property-property correlation to overcome an extreme scarcity of data. In effect, we're doing 2 interpolations. We're going to do one interpolation going from composition to ability from welding, then a second interpolation from ability for welding to ability from printing, and stacking those 2 interpolations together gives one mathematically impossible extrapolation from composition over to ability for printing. So that's just one example of how we're going to be exploiting property to property correlations to overcome this sparsity of data. Now, our tool is able to identify these automatically. We don't actually code this in. It goes and notices that this exists and then exploits it. And this is just one of several property-property correlations that we're going to be exploiting in order to design the alloy. Now, with the machine, or that being the generic machine learning framework, we can look at the specifics for this system. And I've got here a list of all of the target properties that Rolls-Royce need the alloy to fulfill in order for it to be commercial, or to be viable for use as in the engine. So up at the top, we've got the cost of the material. And this is always the most important one, that it's absolutely vital that the material is cheap enough to be commercially viable. And the next down is the density. This is in effect the weight of the component. We need the component to be light enough that the plane will actually be able to take off from the ground. Going down a couple more, we've got the number of defects. So this is actually the measure of how well it performs in 3D printing, how many sort of cracks are formed in the defects. We need a small number of those. And then down the bottom, we've got various parameters about how strong the material needs to be. So I've got listed here just the targets that the Rolls-Royce engineers need us to get correct. But then off the bottom of the slide, we're going to have another list of properties that we're going to be using as proxies to exploit property to property correlations to help predict some of these. So welding was one of them. That's off the bottom of the slide. Rolls-Royce don't care how weldable the alloy is. So it's not a target for it, but we're going to need data for it in order to help predict the number of defects. And there's a few others as well. So we had to go off and collect data for all of these different properties, and that can come from a variety of different sources. It can come from the Rolls-Royce have an internal database of alloys they've looked at in the past. There's a lot of scientific literature out there that we can scan, and there's various databases you can purchase from companies. So we had to go and get all of that data to train the machine learning model for all of these and the proxy properties off the bottom, get our machine learning model up and running, and then we could use it to design a material. And this is what we designed. We've got 10 different elements in this alloy. Now it's chiefly a nickel alloy, which is the balance element, the one at the bottom middle there. But you see there's 9 other elements in there that are all required to get the correct properties. Now, a 10 component alloy is an awful lot. You'll typically find the most advanced commercially available alloys of around 6 elements in. And that restriction is just because of the amount of time it takes to search through a very complicated landscape of all those permutations. But because we were doing machine learning, we had a great opportunity to search through a broader landscape. We had to develop something that's more complicated, but because we were going into that virgin territory, then there is this opportunity to discover something better. Now, down in the bottom right, we've also specified the process, or some of the processing variables. There's several others off the slide, but you see I've just written down a couple of them here. There's the exposure parameter. It's a bit like how much power you put through the laser, and also one of the heat treatment temperatures there. We managed to specify all those, but at this point, what we want to do is see if the alloy actually works in real life. And so we passed it across to our friends at the Rolls-Royce University Technology Centre. It's a group led by Howard Stone, who went off and printed this alloy and helped test some of its properties. Now, the first thing we can do is, well, they went off and printed it, and then the first thing you do is look at it under a microscope, and this is what you get. And at the first glance, it doesn't appear that there are any big cracks that are formed in it. So it looks like it's not been a disaster when we printed it. But you can also see that it's got sort of little black splodges in. And what's actually happened here is the metal has phase separated into two different components, but the presence of that those black precipitates there is absolutely vital, because they actually give the material its strength. It's much actually like a concrete, that's made up of cement and aggregate, the stones, and as a crack goes through, then it stops when it comes across one of those stones. And these precipitates act in a slightly similar way in the alloy. And so we're very pleased to see them. We also measured the length scale of them carefully, because we kind of know the correct length scale we were looking for, and it is about right. It shows we've got the heat treatment for the alloy about correct. But really importantly is how well can you print this material? What's the quality of it, the number of defects formed? And it doesn't look like there's too many, but we should measure it more formally. So I've got here a graph of the percentage of defects on the y-axis versus the exposure parameters. That's like how much power you put through the laser on the x-axis. And we recommended a exposure parameter of 0.8, but because this is one of the most difficult aspects of the project to get correct, and the machine learning told us it wasn't very confident about, we paid quite a lot of money for the alloy to be printed at several values of the exposure parameter, so we could better understand what was going on. Now, we want a small number of defects. We want to be at the bottom of the graph, and actually the target was to be within that grey shaded region of the graph. And you can see from the magenta points there, the experimentally measured values for the number of defects, that indeed at our specified exposure parameter, that indeed the alloy did have a small number of defects. It's within the specification, so it was absolutely great to see. Whereas over on the left, if we had got that exposure parameter a little bit wrong, then you can see there's too many defects and the alloy would not have worked. And so this is just one of many different properties that we experimentally measured. We've got another one here that's not enough time to talk about, but if you want to read more about them, you've got this peer-reviewed paper down here. And to suffice to say, the alloy did work in this case. We measured 8 properties and they all worked, and the alloy is now being further considered with Rolls-Royce for some additional land-based testing. So that was a fantastic project. It's a real poster child of ours for what we can do with impossibly small amounts of data. But our method is completely generic. It doesn't just do alloys. And I just flash up here some of the other applications of our technique in companies that we have been working with. Some of them are alloys and some of them are not materials at all, such as working with the Ordnance Survey on autonomous cars, and Samsung with batteries, and a wonderful paper we did with them, and printer inks and so on. Now, at this point, I thought I'd take a sort of interlude from the science and have a quick look at sort of what we've been doing behind the scenes up to this time in terms of, commercializing this work. everything that we did in the university setting. So I thought I'd start off here over on the left in 2013, which is when we started off the very first project that I did with Rolls-Royce on materials design. So a chance encounter with one of their PhD students when they're asking about a completely different bit of maths, actually. And then I learned at that point about how they were trying to design alloys that would fulfill multiple different criteria. And so I recommended machine learning to them that I knew nothing about, but we had a lot of fun doing it. And we designed a couple of alloys for them that worked and were patented. But at that point, we weren't at all doing those property to property correlations. That came a little bit later when I went off and I got some additional funding, a little bit from Rolls-Royce, and also got a PhD studentship sponsored by a BP up in a little bit later, Samsung, where I started to learn about the opportunity that there was in exploiting those property to property correlations. And we were trying to develop the maths in order for the machine learning to learn from them all by itself and exploit them. So after a couple of inevitable false starts, we got there in the end and had a couple more successful projects, at which point I was fortunate that on the basis of the strength of that previous work, I applied to the Royal Society for the University Research Fellowship that Jin mentioned. I was very grateful that I got it. I'm still being supported by it right now. And it was under, at that time, the headline of concurrent materials design, where the idea was that rather than when an engineer designs something, they have to look up in a sort of yellow pages in a dictionary of pre-existing materials and select the one that is most suited for the purpose. But they can't ask for a new material to be made because it would take 20 years. But using machine learning, we were able to get that development span from 20 years down to 2 years or so. So you can envisage that an engineer could ask for a new material to be created at the same time as a new product, and thus really bring materials into the heart of the design process. And at that time, we called it concurrent. Then I was fortunate, I got quite a large grant from Samsung Electronics, with which we were tasked with, again, doing property to property correlations. But for the first time, one of those properties was not experimental data, but was first principles computer simulations, where that has the advantage that the computer simulations are a lot cheaper to do, maybe $100 or so, versus making a new battery, which might be $50,000. And you're able to do the computer simulations on demand, quicker for the batteries you are currently interested in. And so we were studying how we could merge in those computer simulations to the whole framework and harness them like another property. And then after this, I was because the method was at this point proving to be very generic and very exciting, we're looking about what other areas could it be applied to. And I was very fortunate that a person at it's linked to the university, Dr. William Baines, very kindly sort of noticed that the same maths could also be applied to drug discovery, and that drug discovery has even more sparse data than in the material sciences, and there's some very considerable research budgets available. So he very kindly introduced me to a sort of a medium-sized startup near Oxford called eTherapeutics, and they contracted me through the university to apply the technique to their data. And it went very well, got a follow-up contract, and it's really great to learn about another area and also see some additional opportunities about how we could further improve our machine learning. And so at that point, in some ways, a lot of the research on the technology was done. We've got it working. We've got a big stack of case studies in different verticals that are truly working, being experimentally verified. And so you could ask the question about, well, we could continue to do this in the university. I could continue to get contracts like the ones with Rolls-Royce and BP and Samsung. But then I'm always going to be limited by the number of PhD students I can have, the bandwidth that I'll be able to cope with in the university. And if I want to really maximize the impact of this technique, then perhaps it's time to take it out of the university setting and into a startup company. So at that point, the university introduced me to several business angels. I met quite a few of them, taking them to lunch. sure, they interviewed me and I did a little bit of interviewing them, was able to get on very well, particularly with one of them, Graham Snudden, and with his help, and he introduced me to my co-founder. We went off and founded Intelligent in 2018. So that's the first part of the sort of commercial history of machine learning technology. And with that, I thought I'd dive back into a second scientific use case that's going to exploit a sort of different kind of knowledge, very close actually to what Raffaella mentioned this morning about uncertainties, before I come back and finish off this timeline. So this is a use case that was actually done within the company and actually in league with yet another company, a drug discovery company called Optibrium that we do a lot of work with. And in this, we were, well, actually one of the Optibrium employees noticed that there was what was called this open source malaria competition that was being run by Professor Todd down at over at UCL, where the idea was to see, whereas they provided some data, you trained your machine learning model on it, you tested or engaged, you predicted some unseen compounds that they had separately measured, you saw how accurate it was. And then for the companies that did, or the organizations that did well, they could then design a new molecule that they would synthesize and test. So this is a very exciting, and we're going to see how we managed to sort of apply our or adapt our technology to do particularly well here. So first off, I've got here a quick schematic about how a drug works, or at least a small molecule drug. The basic idea is that you inject the drug on the left, that's an adrenaline molecule, and then it affects the behavior, the activity of certain proteins in the human body. I've got just one of those here, but there's actually about 10,000 proteins to consider in total. And in turn, those proteins have an effect on the human body, which in this case would be to run quicker. Now, there's two big problems here, and we're just going to be focused on the first one, which is, can we predict how a certain drug molecule affects the behavior of the proteins? But there's another equally big problem of how do the proteins affect the human? And we're going to pretend, or somebody else has solved that on our behalf, where we know what proteins we need to affect and which proteins to not touch to avoid harming the human. So we're going to try to develop our machine learning tools. It's going to take in molecular descriptors, such as the number of atoms in or the number of carbon atoms in the molecule, the number of aldehyde groups, etc. There's actually 320 parameters we use to describe the molecule, and how that then affects the behavior of 10,000 proteins in the body. Now, you can imagine this is a huge database. It's actually very sparse. They're typically about 0.05% complete, but the correlations between protein behaviors are very strong. So there's a fantastic opportunity to take advantage of those property-to-property correlations. But say we trained our machine learning tool, and then here we've got a graph of the activity, or on the x-axis, sorry, we've got 4 different drugs that we're currently considering. And on the y-axis, we've got the activity against, or how it changed the activity of one certain protein. One thing that is very particular about our machine learning tool is it not only makes a prediction of the activity level, which for these 4 bars is going to be the central value, but it also predicts for us the uncertainty in that predictions. That's going to be the sort of plus or minus 1 standard deviation here. Now, that uncertainty can typically arise from 2 places. It could either be that the underlying training data had a lot of noise in it, and when we took an average through it, we got a sort of standard deviation in our mean. Or alternatively, when we're going out and designing completely new compounds, we're extrapolating out to them, and we just don't know if the curve goes up or down or where it goes. And so we've got both of those sources of uncertainty here encapsulated in this error bar. Now, if they were the 4 drugs that we predict, or the activities we predicted, we can now imagine that perhaps in the future, the experiments have now been done, and it gave us these orange results here. And if we have made good predictions of those uncertainties, and we claim that we can, then we should usually find that those orange points should be sort of within the error bar. So they're almost distributed uniformly across it. And then when we are typically measuring the quality of our machine learning predictions, then we're making the predictions, comparing against the blind data, the orange points, and we're measuring the length of those grey arrows. And so what we're going to do is we then, of course, you'll sum over the lengths of all the grey arrows to get an overall sort of error in your machine learning tool. But we can see a striking sort of a link that the length of those grey arrows is typically going to be around the kind of the length of your uncertainty error bars there. And so we actually have a bit of additional knowledge about the quality of our machine learning predictions from our understanding of that uncertainty. And this will let us play a really magic, though sneaky trick, which is I could make predictions for these drugs and then say, hey, I'm only going to tell you the 75% of them I'm most confident in. I'm going to say for drug number 3 here, it's the one with the largest error, but I'm not really confident in it. So I'm just not going to tell it to you at all. So we can cross that one out. And then we can see that the lengths of the remaining grey error bars are shorter, so they've got higher quality predictions. Or we could do the same trick again. I could tell you just 50% of the predictions, or just 25% of the predictions. And by doing this, we've made the typical length of our grey error bars a lot shorter, but with a sacrifice that we're not going to be telling the end user about as many compounds. So this is indeed a magic if sneaky trick. And then what you can do is draw a graph here of, on the y-axis, I've got a sort of measure of the quality of the results, the length of those grey arrows, where if I'm at the top, we're getting good predictions. If I'm down the bottom, they're not so good. And on the x-axis, I've got plotted here the amount, the number of the, or percentage of all of the drugs that I'm actually telling the end user. So over on the right is this good, honest way of using this, when I'm going to predict everything, we calculate the quality across all of those drugs, and we get a certain quality value. But then if I start ejecting results in order of their uncertainties, then we can see that actually the quality of the results goes up. And it goes up to a very sort of high level. It's almost perfect predictions if I'm only telling you 20% or so of the predictions. Now, it's not necessarily the case that this curve would go up. If our uncertainty predictions were absolutely awful and actually sort of the inverse of what they should be, then initially on the right-hand side of this graph, we'd be rejecting the good results and leaving the rubbish behind, and the curve would go down. But you see that the very fact that it goes up is because we're making really good, have a very good understanding of our uncertainties. However, you might be concerned I'm still cheating, that I'm not predicting the most difficult drugs in the world, and I'm almost sort of using statistics in a cloak and dagger way to try to fake and make it look like we're getting a better prediction. And in a way, yes, we are, but in a more important way, no, we're not. Because the calculation, the prediction of this R-squared is something that maybe statisticians and machine sort of learning developers are interested in, and getting that R-squared as high as possible. But the actual end user, the person that's going to be making this drug, is not interested in the value of my R-squared. What they're interested in is, does this drug actually work, yes or no? In which case, the wise person would be telling them drugs over on the left-hand side of this graph and just ignoring the ones on the right. And this is going to work in real life, because when we're going to try to be discovering new drugs, we're actually trying to cure a new illness for which no drugs currently exist. But it's likely that there are quite a few drugs out there that would work fine. I've got an example here of, if you have a headache, you could take aspirin, you could take paracetamol, could take ibuprofen. They're completely different drugs. They work in completely different ways in the human body, and all of them would cure the headache. Or if you got COVID, it was an absolute emergency to find a vaccine, and to sort of win, to save the world, we didn't need to find all of the different vaccines. The prize really was to find the first vaccine. And so we can see that there's typically a lot of possible solutions out there, and we only need to find one of them to actually be commercially successful. And so we're going to take a gamble that at least one viable solution lies over on the left-hand side of this graph, and that should be the one that we tell to the final end users, the scientists, to the customers, because it's the one that might actually work in real life. So that proves to be very effective, both in materials and also drug discovery. And we used it to great effect here in this open source malaria competition, that this is the molecule that we proposed for them. So it's our cells intelligence alongside Optibrium. And then the Professor Todd et al. Went off and paid for the drug to be synthesized. They measured its effect on malaria, and it's in green because it worked. Now, there are three other, well, was it two companies and one other individual who sort of got through to the final of this, and their predictions across a sort of a whole family of drug were similar in quality to ours. But they, unfortunately, it seems, did not have a good grasp of their uncertainties. In fact, they didn't know what they were at all. So when they went off and predicted molecules, it appears that they went and predicted something that had a fantastic expected value because it was extrapolating way beyond anything they knew, but probably also a massive uncertainty that they didn't understand. But then these are the drugs they predicted, and ultimately, when made, they didn't actually work. And so we're very proud of this, that it's really showed about how, although we might get similar quality underlying predictions to this lot, how with our good knowledge of uncertainty, we're able to drill down and tell them the most useful, the most probable drug to work. Right, so with that, that's the second part of the science. I thought I'd just have a finishing off here with the final steps in commercialization, that I've now founded the Staff Intelligence in 2018. I've got a co-founder, Ben Pellegrini. He's not from the university, he's got a different software background. And the first step is we were very fortunate that we could bring across some of the already sort of established customers from the university and port them across into our company. And this, of course, provides a very helpful source of initial revenue for us, and also make sure that the company is then going to be focused on developing technology that's focused on customer needs rather than perhaps our sort of scientific dreams. Now, going on from that, we then worked hard, and that was a sort of excellent springboard to go out and get many other customers. And we did lots of consultancy contracts to a variety of excellent customers here, which were very helpful to help us sort of better understand the whole material and chemicals landscape. It was very helpful to learn about more customer problems, about additional technology that we needed to develop to improve our machine learning, and to also help us develop our underlying software stack. So the consultancy work is all well and good, but it's also ultimately going to be a little bit limited in the impact that it has, because the amount of consultancy contracts you can do is always going to be limited by the number of people that you employ. But much more, even more effective would be to develop our machine learning tool as a software package, which we can then license to the customers and they can use. And then the number of software packages that we can sell becomes relatively independent of the number of staff that we have. And so we're able to develop the software during that period of consultancy, and also build up some really good relationships with those customers, so that several of them were then the first customers for our software product. And so we had a sort of a ready set of customers ready to go. And then at the same time, we were also working with the drug software company Optibrium to develop a product called Sorella, which they would go off and sell. And so this case, in this instance, we decided that as intelligence, we wanted to focus on the machine learning and our domain of expertise, which is materials and industrial chemicals. And to enter that drug space, it was better to do it through another partner that already had an established reputation, already had a big sales base, and they would do a better job of it than we could. And so we opted to act through the reseller. That product, Sorella, was released in October, when was it? No, early 2021. And at the same time, we were also pushing hard to further develop our own machine learning product. That at the, for that first year or so of licensing the product, it was typically being licensed to the 1, 2, 3 bench scientists in the companies that we had been doing the consultancy contracts with. However, that's of belie there's a huge opportunity in those companies. Many of them are really high quality, so international conglomerates with tens of thousands of scientists. And can we not sell to all of them rather than just 1 or 2? And so we then try to flesh out our products and add many other features that you'll need in an enterprise style license, that you need to be able to get the materials, the databases to be shared between teams, but at the same time security, so it doesn't go too far. You need lots of security type setup around there, and different types of users who have different levels of access. And so we had to set all of that stuff up. But we were fortunate that we were then able to take, or we're in the taken already a couple of the small scale license software licenses that we had to convert them into much larger scale enterprise licenses, which of course also from our point of view means that we're going to be able to get much higher license fees, which is fantastic. And at the same time, we have to see the impact of the code or the methodology continue. And then finally, hidden a bit behind the Zoom thing is that we've also teamed up with another large company called ANSYS, who sell a lot of simulation software, in order to be able to use our machine learning tool more around simulation data and speeding that up rather than experimental data. And that product's going to be out in a few weeks' time. So we're very excited to see how that goes. So that's a quick story of the commercialization post founding of the company. Cool. With that, I should summarize that I've shown today how we've developed this machine learning tool that's specialized on handling experimental data and has a particular prowess at exploiting property to property correlations. I then showed its uses, firstly on designing the alloy for direct laser deposition, where we had an impossibly small amount of data to train off. And secondly, how we exploit our knowledge of uncertainty to give really robust results to our customers. And I've shown how the result is entirely generic and how we've been able to already roll it out across many different domains, and how we're driving forward the impact of the method with its commercialization through the startup intelligence. So I'd like to thank you again all for your attention. I hope there's a few minutes for questions.
Yes.